Welcome to Pomodoro Joe for Monday, September 25th, 2023. Today we're looking at LeetCode problem 389. Find the difference. This is an easy problem. You were given two strings, S and T. String T is generated by randomly shuffling string S and then adding one more letter at random. Return the letter that was added to T. Okay, and we have some examples, ABCD and ABCDE. So the random letter added to T was E. Cool. Now it looks like our lengths are pretty long. We can have characters or strings up to 1,000 characters. So let's jump into this one. We'll put 25 minutes on the Pomodoro timer and get started. Now with this one, there are so many different ways to do this. So let's explore a couple ways. First way is the straightforward way. We'll go through and we'll just count all of the characters, or we'll count how many of each character we have in string S. Then we'll go through string T, doing the same, and see which one has the difference. All right, so let's have a dictionary that stores our key value pairs. The key will be the character, and the value will be the count. So let's have S counts. And let's see, this will be a default dictionary. And this will be of type int, because our key will be the character and the value will be the count of that character in our string S. All right, then we could also do a T count and do the same, but I think what I'll do instead is I'll have my S count, just count up all the characters in S, and then I'll go through my T count or my T string and we'll reduce the counts from S. And then we'll look for the one that has a count of -1. All right, so for every character in S, our S counts for this character will increase by 1. This is just keeping the count of every character in S. So for example, ABCD will have A is equal to 1, B equal to 1, C equal to 1, D equal to 1. All right. Now we'll go through T. For every character in T, well, let's subtract that character from our S count. So S count. So our S count for this character will be reduced by 1. And then finally, we'll have to go through every character in our dictionary to find the one that has a count of -1. So essentially, all the characters will have a count of 0 once we've added all the characters from S and then subtracted all the characters from T. We should have zeros for every character except the one that was added to T. All right, so then for every character in our counts, if our S counts for this character is equal to -1, then we found our character and we can return this character, return C. Now, we should never get out of this, but just in case, it's always good to have some return value, just in case for some reason we didn't do this right. Let's return something. So we'll just return an exclamation point. Okay, so let's run this, see how we do. S counts, plural. All right, try that again. Okay, so this works. Let's see if we can pass all the tests. And we do pass. Let's see, and we do okay. We beat 60% for runtime and 40-something% for memory, so that's not too bad. All right, let's jump back here. Another thing we can do, super quick. So we can use the same basic algorithm, but instead of doing the count ourselves, we can use the counter. So if you look in the collections library, you'll find something called a counter. The counter basically does this exact thing for us. We can just say counter of S. So this will be counter of S. And then we'll probably want to do the same thing with T. So we can do T counts. And this will be a counter of T. And then instead of subtracting our T here, let's just go through for every character in our S counts. We'll just check to see if the S counts is equal to our T counts for the same character. And if it's not, then we'll return C. So this is basically the same that we did before. We're just using this Pythonic thing called a counter, which is a collections library data structure. All right, let's try this again. I'm missing my colon. Try that one more time. Oh man, so many typos. And we are failing. That's weird. Why did that one fail? I know why this failed. It's because we're only going through the characters that are in S. There could be a character that's not in S, that's only in T. So what I really need to do is go through every character in my T counts. All right, try this again. There we go. Now let's submit that. Okay, and that seems to work. And it does better than our previous solution, just by a little bit. Now we're at a 78% for runtime and a 99% for memory. Wow, that's actually really good for memory. All right, let's jump back and we'll do this one more way. So one more thing we could do, we're just trying to find a character that's in T that's not in S. So we could sort all of our characters and then just go through and compare every character in our sorted version of S to our sorted version of T. When we find one that doesn't match, then that's our added character. So let's do this. We'll have a sorted T and a sorted S. So we'll just call sort or sorted on S and sorted on T. Now for every character in, actually I'm looking for an index, so I should do every index in range the length of S if our sorted S at this index doesn't equal our sorted T at this index, then that's our character. So we can return, let's see, we'll have to get the character at sorted T, index I. Now if we make it all the way to the end and we didn't find one that was mismatched, that must mean that this character, the very last character in T, is the new character. So then we return sorted T at the last character. It's at -1. All right, try this. Okay, that seems to work. And we pass, but we don't do very well. We only beat 28%, 24% for runtime and 76% for memory. So that is not the best solution. So let's just do a quick big O notation analysis here. In our very first solution, we go through every character in S. So for every character in S, and we go through every character in T. Now, let's just say S is length n. There are n characters in S. That means there are n plus 1 characters in T. So essentially, they're both length n. I mean, if you had a million characters, a million and a million and one, not a big difference. So S and T are essentially both length n. So we go through length n for S, so O of n. We also go through length n again for T. So that's basically n plus n. In big O notation, that's a wash. You just call it O of n. There's no difference. So in this case, we go through n characters in S, n characters in T, and then we just go through 26 characters, basically the characters of the alphabet, to find our difference. So for this is a big O of n solution. So this is a linear runtime solution. Now if we look at our next solution that used counters, now I don't really know what's going on under the hood of these counters, but I can assume that they have to go through all the characters at least once. So this is probably also big O of n. So another linear runtime. So these are similar in our big O analysis, and yet the difference in their runtimes is significant. We go from a 60% to a 78%. Now the main difference is these counters are going to be optimized. These are probably implemented in a lower level language like C. So these are going to be optimized to do exactly what we did using our less optimized default dictionaries. So that's why this one does a lot better. Now our next one, we sorted S and we sorted T. So in a sort algorithm, when you sort something, you have to go through every character at least once, and you have to sort them. You have to put them in the right place, which is a comparison. So generally, a sorted like this is going to be n log n procedure. And we do it twice. So we have 2 n log n, but again, you can drop the 2. So this is going to be an n log n runtime, which is significantly more, well, I shouldn't say significantly. It is noticeably more than just an O of n runtime. Okay, so that's just a quick analysis. That sort of explains why this one does worse than the other two. Not a great analysis, but hopefully that makes some sense. Okay, so I guess that is it for me. I hope you enjoyed this. I hope you had fun. I hope you learned something. I hope you can go out and write better code.